Well, those three effects were all produced by light, and we will be looking at each of them in turn later in this program, a program that's going to be concerned with modeling the behavior of light. Now, you may have got the impression from the text that light is something that we don't understand very well. But in fact, that's not true. It's one of the best understood branches of science. The reason you might have got the impression that it's not very well understood is that we don't have a single model for its behavior. Until the end of the 19th century, all of the properties of light could be explained in terms of a wave model. But at the turn of the century, a new phenomenon was discovered known as the photoelectric effect. And this was much easier to explain in terms of a particle model. In the photoelectric effect, light causes electrons to escape from the surface of a metal.
Well, here's a piece of zinc, and if I allow light to fall on this zinc, then I should be getting electrons boiling off. The trouble is, I can't see the electrons coming off. But if you remember that electrons carry charge, then a loss of electrons means a loss of charge. So I want to detect that loss of charge. And I need a charge detector. And that's exactly what this piece of equipment is here. It's a gold leaf electroscope. Just watch this. If I take a comb and comb my hair, produce a bit of charge, rub it down this plate. See, what I've got is a plate connected to a metal stem, and there's a gold leaf attached to the plate. So the electrons go onto the stem and the leaf, and they repel each other. If I earth the plate, the electrons escape through my body to Earth, and down goes the leaf. So all I have to do now is put the zinc on top of the plate, charge it up. So now I've got excess electrons on the zinc, and allow the light to fall on the zinc. Well, bring up the light, and absolutely nothing. Well, perhaps I haven't got enough intensity. Well, okay, let me hold the lamp very close to the zinc. And still nothing. But do you remember that early S101 program where we said that you could get really intense and concentrated beams of light from a laser? Well, as it happens, I've got a really high-powered laser here in the studio. In fact, it's so high-powered that we've deflected the beam through a right angle so that it doesn't get into anybody's eyes. Now, if I put the zinc under that, then surely that will have an effect. But still nothing. Well, I could only do this demonstration with such confidence because I tried it earlier today and I knew it was going to fail with this intense red laser beam. But just look what happens if I allow the light from this mercury source, this mercury vapor lamp, to fall on the plate.
Now, there's only a tiny mercury bulb inside that large protective casing. And in fact, I've done a calculation that indicates that 10 times more light was incident on the zinc from the red laser beam than from that mercury lamp. So an intense red beam doesn't produce the photoelectric effect, but a weak mercury lamp light does. So whatever else it is that determines whether the photoelectric effect occurs, it's not the intensity of the light that matters.
Well, here's another clue. Let me charge up the zinc again. Now, what I've got here is an ordinary piece of glass. I'm going to hold it over the top of the zinc and move the whole thing underneath the ultraviolet light. And nothing happens. But if I move the glass, and I can stop it. So whatever it is that's causing the leaf to fall, it can be blocked by a piece of glass. Now, actually, it's the invisible ultraviolet component in the light emitted by this mercury source that is causing the leaf to fall. And it can be blocked by glass in much the same way as you can stop yourself getting sunburnt by the ultraviolet light in the sun by sitting behind a window. So I can get the photoelectric effect to work for this piece of zinc as long as I use ultraviolet light.
But why do we like to think of the photoelectric effect in terms of a particle model? Why not use a wave model? Well, let's think about what a wave model implies. On a wave model, the colour is determined by the wavelength of light. That's the distance between two troughs of a wave like this. And you could think of this wave as representing ultraviolet light. Red light, on the other hand, has a much longer wavelength, and in fact is about a factor of 2 longer than for ultraviolet light. But the amount of energy carried by one of these waves isn't determined by the wavelength, it's determined by the amplitude. And that's related to the vertical distance between troughs and crests of the waveform. So these two waves have about the same amplitude. That means they carry the same amount of energy. Now, in our experiment, the intensity of the ultraviolet light was in fact much smaller than for the red light. And that means that what we'd expect to happen on the wave model is the red light would produce a photoelectric effect, but the ultraviolet light wouldn't. That's just the opposite to what we observe. Well, what about a particle model? Think of this square as representing our piece of zinc, and these black counters as being some of the electrons in the zinc. Now, if we think of light as particles or photons, and if we assume that the ultraviolet photons have more energy than the red photons, then we can explain the photoelectric effect quite simply. An ultraviolet photon carries a large amount of energy. When it interacts with the electron, it gives it enough kinetic energy to escape. On the other hand, a red photon doesn't carry so much energy. When this energy is transferred to an electron, the electron has insufficient energy to escape. It just bounces around in the metal, and the energy eventually ends up with heat. Now, the important point is that however intense we make the beam of red light, the energy of each individual photon is exactly the same. We just increase the number of photons present. And that means that we cannot produce the photoelectric effect. Not enough energy goes to the electron to allow it to escape. So we do see the photoelectric effect with high-frequency ultraviolet light, but we don't observe it with low-frequency red light. Obviously, there must be some threshold between the two frequencies, and that threshold frequency depends on what material we're using.
And that's important if you want to tap the energy, for instance, available in sunlight. You have to design your photoelectric material so that it responds not just to the ultraviolet end of the spectrum, but also to the red end of the spectrum. And that's precisely what a solar cell does. I've got 3 solar cells here, all connected together and connected by some wires to a little motor. But there's nothing else connected here. There's no input circuit to it. If I turn on the red light, then the motor starts turning and it lifts the weight. The system's doing work. Not exactly the most useful form of work, but work nonetheless. Now, what exactly is a solar cell? Well, it's a crystal of silicon, the same stuff that transistors are made of. But we have the crystal divided into 2 halves. And the effect of this is to create a junction region with a strong electrostatic field across that junction. Now, if a photon enters this junction region, it can eject an electron by the photoelectric effect. And, of course, because of the strong electrostatic field, the electron's whisked off in this direction. So if we now connect up an external circuit, then the electrons can flow around this circuit, and that can do work. So you see, the photoelectric effect is not just an academic exercise, it also has practical applications. A whole array of photocells like these can be used, as here, to provide power for a satellite orbiting the Earth.
We deliberately started this program by talking about the photoelectric effect because that's easier to explain in terms of particles, and we thought that that would be the less familiar model. But now let's think about waves. We showed you some ripple tank photographs in the audio vision sequence, which showed that the behavior of light could quite easily be modeled by the behavior of ripples. Pictures that showed that ripples could be reflected just like light, and also pictures that showed the refraction of ripples, very similar to light. But pictures like this can't convey the motion of the water. So let's have a look at a ripple tank in operation. Simple parallel waves, and the bright lines correspond to the crests of the waves. But how are we producing them? Well, they're actually being projected onto the surface of this screen by a mirror. The water is actually in this shallow tank, and you can see that at the moment we're producing parallel waves by vibrating a paddle backwards and forwards. But that's not too interesting. Let me show what happens when we put a barrier to obstruct some of the ripples. There's quite a strong beam propagating straight through the barrier, and it's probably easiest to follow if you move your finger across the screen like this. But there isn't a sharp edge to this beam. The water waves are being diffracted around the edge into this region here. And I think this is even more pronounced if I make the slit somewhat narrower. You can see that now we don't have a pronounced beam in this direction. Instead, the waves are spreading out uniformly in all directions. Well, that's a single slit. What happens if I open up a second gap in the barrier? Well, you see that the pattern's somewhat more complicated now, but if you follow the waves across, I think you can see that there's a clearly defined set of waves traveling in this direction, straight out from the slits. There's another set of waves coming up here. There's another set of waves going down here. And there are a couple of others as well. But the most interesting thing is that between these regions, at places like this and this, the water appears to be quite still.
And we can do the same sort of thing with an optical setup. Here, the plane waves produced by a laser beam striking a double slit looking something like this, and then the light propagating onwards and producing an interference pattern like this. Now, there are more spots there than you were seeing in the ripple tank, but essentially it's the same sort of thing. And it's very similar to what you did with the home experiment, where you held up the double slit to your eye and looked at a distant light source. Again, you saw this pattern of maxima and minima. So how do we explain this so-called interference pattern?
Well, let's have a look at the ripple tank again. And this time, concentrate on a point like this, a point where there's a strong beam of water waves. This point actually lies along a horizontal line that passes through the center of the two slits. And that means the point must be equidistant from both slits. Now, arriving at this point, there must be a wave coming down a line like this from the top slit, and a wave coming along a line like this from the bottom slit. The question is, how do these waves combine? Well, let's look at the two waves in more detail. The wave from the top slit might look something like this, and the bright point indicates the point we're actually interested in. The wave from the bottom slit would look like this. And note that they're going up and down in step. That's because the path difference from the two slits is the same. To find the combined effect, we need to add the two waves, to superimpose them. Here they're constructively interfering, and we get a wave which is twice as large as one of the waves on its own. So we're getting constructive interference at this point. Now, we also have a strong beam here, where we're also getting constructive interference. But this time, the difference in path length between the top slit and the bottom slit is a wavelength, so the waves again arrive in step, and that explains why we get a strong beam. But what's happening at a place like this, a place where we have no wave apparently propagating? From the top slit, we could get a wave something like this, viewed in cross-section. From the bottom slit, a wave like this. But note that now they're out of step. That's because the difference in path length from the two slits is half a wavelength. If we add these two waves, then they interfere destructively. We get only a very tiny wave passing through that point. So we get destructive interference at a point like this, constructive interference at a point like this, and of course, at points in between, we'll get some sort of partial cancellation of the waves. But we can explain all of the interference effects that we're seeing here in terms of the interference of waves from the two slits.
Now, that was the situation in which we produced the two interfering sources by taking one wavefront and putting a barrier in the way with two slots in it. But we don't have to do it that way. Have a look at this. I've got a single microscope slide here, a piece of glass, and I'm going to put a second microscope slide on top of the first. But I'm going to put a little bit of paper in this top end. Now you see, I've got a wedge between the two microscope slides. I'm illuminating these microscope slides with red light from this light source here. And if I look down the microscope, just as before, dark and bright fringes. So what's happening in this situation? Well, what we've got is light coming in and striking the bottom of the top plate and being reflected back up towards the microscope. But only a fraction of the light does this. Some of the light goes straight through and hits the top of the second plate and is then reflected back towards the microscope. So here we've divided the amplitude of the light wave. Now, if the path difference between these two light waves is exactly half a wavelength, then the two waves will be out of step with each other and we'll get destructive interference. A bit further along the wedge, there'll be a position where the path difference between the light from the top plate and the light from the bottom plate is exactly one wavelength. So now the waves reaching the microscope are going to be in step, and we get constructive interference. And the further I move along the wedge, the more I'm going to get dark and bright fringes. So if I know how well spaced the fringes are, and I know the wavelength of the light, I can calculate what this wedge is. Furthermore, if I change the wavelength, put in a blue filter so I've got blue light, shorter wavelength, then I don't have to go so far along the wedge before I get half a wavelength out of step. So what do you think is going to happen to the fringes? Go back to the red, the fringes are wide again. The blue, they're close together.
Well, this type of interference is very useful when testing lenses. When a manufacturer makes a lens like this, he wants to know that the curvature of the surface has exactly the right value. Well, how does he test that? He makes a lens plate, which has exactly the opposite curvature to that required on the lens. Then, if the lens is put on the top of the plate, we can look for fringes to see how good the match is. Well, in this picture, there are quite a few fringes, so the match obviously is not yet good. So the lens needs a bit more polishing, and after it's polished, it's tested again, and the presence of just a single fringe here indicates quite a good match between lens and test plate.
Well, we said right at the beginning of this programme that light was one of the best understood phenomenon in the whole of science. Yet here we've been a little bit schizophrenic about it. On the one hand, waves, and on the other hand, particles. So we thought we'd finish by showing you a demonstration which drew these two models together. I've got a very simple setup again. The laser producing plane waves, striking a double slit and giving rise to the interference pattern, maxima and minima, just as you saw before and just as you saw in the ripple tank. So this whole part of the demonstration, laser, beam, diffracting object and pattern, can all be understood in terms of the wave model.
But if I remove this screen, then the interference pattern can fall on a detector. It's actually a photomultiplier, a glorified photocell, which works on the photoelectric effect. So it is relying on the particle model for its explanation. Now, the signal from the photomultiplier is fed by these cables to a pen recorder. And there's quite a large vertical displacement of the pen at the moment, but if I interrupt the light beam in front of the detector, it drops down. And you can see that, obviously, the pen is responding to the amount of light falling on the photocell. Now, what I'm going to do is to make the photocell traverse through the pattern and look at the output of the photomultiplier. Okay, I'll start at this fairly faint region of the pattern, and we'll see what happens. As we scan through, we get alternate regions of high and low signal. Bright gives large signal, bright, dark, bright, dark, bright, dark, bright, dark, and so on. We've plotted out a pattern here which looks very much like the pattern that we would predict from the wave model. But I said that this was a particle detector. So where does the particle model come in?
Well, they come in when the photons are detected by the photosensitive surface. You see, each photon ejects an electron, and the electrons eventually find their way down to the end of the phototube, and they give rise to an electrical signal, which is what was being fed onto the chart recorder. The problem is that when you've got a really intense beam of light, in a second, say, you've got millions of photons arriving in that time interval. So you don't really stand much chance of detecting individual ones. All the chart recorder can do is average them out. So to give ourselves some chance of detecting individual ones, what I've got to do is reduce the intensity of the beam. And I can do that by introducing a filter. Now this filter should cut down the beam by about a factor of 1,000.
Well, the pattern is really quite faint now, and probably too faint for you to see. But possibly now we have a chance of detecting individual photons. This time, the signal from the photomultiplier is being fed to an oscilloscope. And as the oscilloscope beam moves across the screen, we get bright pulses every time a photon is detected. But let's listen to that on a loudspeaker, because it makes the demonstration more impressive. You can hear the little clicks of sound, each corresponding to the arrival of a photon. And those clicks are synchronized to the little flashes on the oscilloscope. Well, at the moment we don't have very many photons arriving in a second, say. Let me try moving to a brighter region of the pattern. We'll see if we can detect more. There. I think you can hear that there are a good deal more photons arriving now. We're getting more clicks per second and more flashes on the oscilloscope. But what will happen if I track the detector through the diffraction pattern? Dark again, only a few photons. Bright. Another dark fringe. And bright again. Well, let me turn off the loudspeaker so I can be heard. You can see that although we were detecting individual photons, as you could actually hear and see, we are tracing out a pattern of bright and dark fringes as predicted by the wave model. So the wave model is telling us how the light travels through the diffraction grating to the front of the photomultiplier, and it's telling us where we get bright and dark regions, but the photon model is telling us just how the light is detected.
So, you see, there really is no contradiction. In fact, if you bear with me, I'd like to tell you a little tale that I heard a short while ago. It goes something like this. Suppose you were trying to explain to somebody brought up in a big city who'd never seen a lion what a lion looked like. Well, you might say its fur's coloured like honey. Or you might say that it had a roar a bit like a motorbike. That doesn't mean that a lion is honey or a lion is a motorbike. It's just that sometimes it's most helpful to think in terms of the one analogy, sometimes in terms of the other analogy. Well, okay, it's a bit of a twee story, but I think you get the connection with light. You see, light is not particles, nor is light waves. It's just that the behavior of light can sometimes best be modelled in terms of particles, and sometimes in terms of waves. So we really get a deepest understanding of the behavior of light if we can somehow use these two models to complement each other.